Okay. And let's see. Okay. So we're doing this handout. Hide that. So we're doing the More Fun with Counting, section 5.6. And so what I'm thinking of doing is not writing on this thing, but writing on the board and keeping this up on occasion until I need that part of the board. And see if this idea works. I'm kind of like playing everything by ear. Okay. Actually, just want to make another check on Megan, just because I think she might have rejoined. I'll try again. Megan, can you hear us now? Just turn your mic on and say yes or no.
Yeah, I got it.
Okay, yay. Okay, cool. Right on, all good in the hood. So here we are. We have some fundamental formulas. Let's see. So question one, I'm going to actually keep the formulas up here and then we're going to use them forever over here. So there's a number of ways to arrange n distinct objects. So a number of ways to arrange n distinct objects. And we really don't have to say distinct. It's quite obvious. Like if we have three of the same object, there's only one way to arrange them. So distinct is kind of important. And this answer is n factorial, which is 1 times 2 times 3 all the way up to the last number n. The second most important formula was a number of ways to select R objects from n distinct objects and then arrange them. So this is a permutation of R of the n objects. Again, understood to be distinct. The formula is PNR, and that's n factorial divided by n minus r factorial. And then the last formula that we need to know is combinations. Combinations of R of the n objects. And this is CNR, which is n factorial divided by r factorial times n minus r factorial. These are the ones we're going to be using a lot. We'll get to the fourth one on this page in a second. So, when objects, order matters. When I permute, or permutate, permute, the same thing, order matters. But when I'm doing combinations, order doesn't matter. But then this last question, number 4, is saying, number 4 down here on the bottom of this PDF, is saying the number of ways to distribute R distinct objects into n different slots. So we think we've been using that a lot. It's not a formula that we really gave. It's a common sense thing. So for example, I have like 6 slots. Say I have 6 slots. I see what's going on. And I want to distribute two distinct types of objects. For example, heads and tails. So I'm putting H's and T's inside the 6 slots. So what I do, draw out the 6 slots. And then I say, well, this can be be H or T. This can be H or T. H or T. H or T, H or T, H or T. So now I have two choices for each, etc. Two choices. So this last thing is saying that the total then is 2 times 2 times 2 times 2, 6 times. In other words, this many ways, 64 ways. So in general, the formula that we're really asking for this question number 4. So the number of ways to distribute R distinct objects. I'm going to say types of objects. I mean, I know it does distinct objects in the handout, but what I'm saying here is that we're not just putting two, like one H and one T in here. We're putting H's and T's in here, but only two types of distinct objects. So like maybe adding this word types might help, because we're not really just putting R distinct objects. We're putting R types of those, like H's and T's. R's can be 2, into n slots. So if we look at this example, we would have 1, 2, 3, ... We would have n slots, and we would have R choices to put in each slot. R choices, R choices, R choices. So if I multiply R times R times R times R a bunch of times, the total is equal to R times itself n times, or in other words, R to the n power. So this is a formula we haven't seen, but it's a common sense formula that we were doing. Say we had a coin that had 3 sides, and we flip it 6 times. If a coin has 3 sides, which is impossible, if a coin has 3 sides, which is impossible, there'd be 3 choices, 3 choices, 3 choices, 3 choices. Oh, wait a second. I just came to think of it. I'm looking at a PDF here on the screen. Are you seeing this PDF on the screen, or are you only seeing the screen, the visualizer, the chalkboard? Do you see a PDF here?
Yeah.
Okay. I was just making sure I'm not being a real total teaching idiot. This is my first time putting the PDF over the chalkboard. There's no handbook on online teaching. I mean, there probably is, but I didn't read it. Okay. Okay. So these are the 4 formulas that we're going to constantly be using. Now let's look at this Chipotle. It's a counting problem. And we have a menu for Chipotle. You can choose your style of meal, your meat, salsa, and if you want some extras. So maybe I'll erase this example here. So the Chipotle problem. How many different meals can we order if you don't want extras and you can only choose one thing from each category? So, does this use any of these formulas? No, not at all. This is one of those common sense kind of things. So we, when you choose your meal, you choose your meal, which is the stuff up here of these 4 choices. Then you choose your meat, which is these 5 choices here. And then you choose your salsa, should you desire salsa, one of those 4 choices. So once we've said that, we've got like these slots. So you think of it as mini task 1, mini task 2, mini task 3. Oh, mini task 1 is to pick your meal. And it looks like there's 4 choices from that top: burrito, tacos, or salad. And then we pick our meat. I guess I'm using the meat word like loosely because vegetarian is actually one of our choices for meat. 5 choices. And then we pick our salsa. And there's 4 choices. So the total is, by the multiplication principle, is 4 times 5. Now, over 8 times 4, there's 80 ways to order something from this meager menu of Chipotle. Okay, question 6. Oh, move this damn there. Question 6. This needs an update. B is no longer a G friend of mine, but my old ex-G friend used to work at Chipotle. She tells me that I have an old menu. True story. Happened a few semesters ago. And sofritas, the organic tofu thing, is now available as a meat option. So now we're going to answer the same question considering this new thing that not only do I have chicken, steak, barbacoa, carnitas, and vegetarian, but I also have this thing called sofritas. So what does that change? The new menu. As I still have my 3 slots, there's still 4 meals to pick, 4 choices. But then for this meat veggie thing, there are not 5 choices, there are 6 choices, and the salsa stays the same. There are still 4 choices, so the total is equal to 4 times 6 times 4. So it only ups this by a wee bit, 96 ways. So this is the multiplication principle in action. So finally, like a more intense question. Let's suppose that how many different burritos can be ordered if the manager says that you can only choose at most 2 different meat options? At most 2 different meat options. So we want to think about this. When we see at most, I said this last class, last Thursday, at most we think cases. And once we're thinking cases, that means we're going to do the addition principle. Whenever we see the word at most or at least, we always chop it up into cases because we're going to make this one job into completely unrelated jobs and then do the mathematics of how to count each job and then add up all the totals in the end, as opposed to multiplying all of these subtotals when you're doing mini task 1, mini task 2, mini task 3, or step 1, step 2, step 3. Chopping this up into 2 different jobs is not step 1 and step 2. That's like job 1 and then completely different count job 2. And in order to count job 1, you might break that up into steps. In order to count job 2, you might break that up into steps. So it might be a combination of multiplication principle and addition principle. But in the end, we add the totals for each case. So case 1, since we can get at most 2 different meat options, there are 2 cases. Case 1, you get exactly 1. And again, I'll put it in quotes. We have this meat veggies. There's 6 choices for your meat veggie, right? The what do we call it? The chicken, steak, barbacoa, carnitas, vegetarian, and sofritas. So that's case 1. And if we do case 1, and only 1 salsa, right? Only 1 salsa and no extras. So if we have exactly 1 meat, and we don't have this option anymore of the meal, what type of meal, because we're saying we're definitely getting a burrito. You know, we're definitely getting a burrito in problem number 7. So there's only 1 choice meal. We're not getting a burrito bowl or anything, but just a burrito. So don't even think about that. That's no longer a choice. So what is a choice is the meat veggie and the salsa. The meat veggie is clearly 6 choices. the 4 actual meats, and then the vegetarian is the 5th, and the sofritas is the 6th. And the salsa, there's 4 choices. So the total number of ways to do this step, this job, my bad, is 24 ways. 6 times 4, which is 24 different ways. So now we need to be a little trickier for the other thing. Case 2. You get exactly 2 meat veggie. And now the question said they should be different. So you can't get steak and steak, because that'll be a different answer than altogether. Because then you'd say, well, 6 choices for my first meat, and then 6 choices for my second meat. And you would lie to yourself and say, 36 choices. But also, it's not 6 choices for my first meat, and then 5 choices for my second meat. That's the wrong answer. Because that would mean if I chose steak and chicken, that would be different than if I chose chicken and steak. And clearly, that doesn't make any sense. Like having steak and chicken on your burrito is the exact same as having chicken and steak. So I can't say 6 choices for my first meat, 5 choices for my second meat. In other words, we need the other option. I am choosing something without any order. Choose a combination. A combination, which is behind the board here, the CNR formula. It is 6, so to choose the meat veggie, the number of choices I have is C62. And C62, the number of ways to choose 2 items from 6 items is 15. We can do the 6 factorial divided by 2 factorial times 6 minus 2 factorial, jazz, blah, blah, blah. We'll get 15. And then we pick our salsa. Our salsa there's still 4 choices. So the total here, is 15 times 4. 15 times 4 is the number 60. Okay, this looks really small on my chalkboard. Can everyone see the number 60, or do I need to just double my font? Well, I can see it when I get closer to the thing. Can everyone say 60? Or do I need to increase my font overall for everything I'm doing?
I can see it.
You see it? Okay. It's good enough to hear one person say that. Okay, so we add up the 2 choices. I have 24 ways to do case 1, 60 ways to do case 2. So then the answer, by the addition principle, is 24 plus 60, which is 84 ways. 84 ways total. There's 84 possible ways to order a burrito that has at most 2 different meat options. So if you interpret this question to mean, what if you don't want any meat or vegetable on there? Then that's a different answer altogether. Then there's 3 cases. But I think it's kind of silly to have a burrito that has not chicken, not a steak, not a barbacoa, not a vegetarian, nothing. What does it have in it? I mean, that's like ordering a burger with no burger patty or a vegetarian patty, just like you know what I mean? So I think this is safe to say at most 2 different meat options means you can't have 0. Okay. Okay. Unless you're that type of person that orders a burrito with nothing but the rice and the what's left, salsa in it. Okay. So the next type of is this block walking. This is coming up on this page, and it's on the book on page 221, but we're going to go over this book example. Maybe I'll move this over here. So we're block walking. So what can that really mean? What do I want to do? Maybe I want to keep these formulas up here, so I'll erase this. So we're walking from A to B. and it's 3 units high and 4 units across. So A is this point over here, B is this point over here, and the rule is we can only move south or east. Those are our only 2 available moves. If I was allowed to move north and west, then there's infinitely many ways to go from A to B. I can go circle around, then go there, you know? So we're going to say we can only go down and to the right. So when we think about it, if I want to count how many paths from A to B, well, you can just say a lot, because there are a lot. Let's look at one example. Let's pretend we went down to and over 3, down 1, and over 1. So what did we do? We went south and then south. Then we went east, east, east. Then we went south. Then we went east. That's one example of a path. How about another way to get from A to B? We can go over 2, down 3, and then over like that. So this example would be I went east, east, then I went south, 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 and then east, east. Okay, in a way more interactive class, which this one isn't because people are really quiet, I would say, what do these 2 things have in common? And then there'd be silence for a minute, and then one person would say, oh, they have the same number of S's in each row. And they have the same number of E's in each row. And they're the same length. So there's some things we know. There's no way it's going to take me longer than 7 steps to get from A to B. And we know it will never take less than 7 steps also. So it's going to take exactly 7 steps. And I'll never exceed 3 south moves. And I'll never exceed 4 east moves. Because if I did a 5th east move, no matter what, I'm going to be out here on the edge of the universe. And if I did more than 3 south moves, I'd be down here. So exactly 3 S's, exactly 4 E's, length of 7. So the new question is, how many ways can I have a word that has length 7 with only 2 letters choices, S's and E's, but I can only have 3 S's? So then you think about this option here. And this is the most wrongest thing to think about. If I choose 7 slots, it's not about how many choices for each slot. Because, again, every one of these problems are think outside the box. Like, think this is good for flipping a coin, great. But this is not good for this type of problem. We need to essentially, I guess the new question is, well, since this doesn't relate, I'll erase this. The new question is, or equivalent question, how many length 7 words have 3 S's and 4 E's? And 3 S's and 4 E's. If I can answer that question, that'll give me how. Because once I make a length 7 word that has exactly 3 S's and exactly 4 E's, that gives me a unique path from A to B. So it boils down to where do I put the damn S's? Like if I know what 3 slots I can choose to put the S's, then I don't have to care about the E's. I know where the E's damn go. So I just focus on the S's. Once I choose 3 of the 7 slots to put the S's, that's how many paths there are. But then you might say, what's special about S's? Well, nothing at all. You don't have to choose S's. Instead, you can choose how many ways to choose 4 of the 7 slots to put the E's. And then you put the E's, you know where the damn S's are. So it's a choose thing. You either choose 3 of the slots, 3 of the 7 slots to put your S's, or do the problem a different way. Choose, that's what the C stands for. Actually, it stands for combination. Let's get to think of it as choose. Choose 4 of the 7 slots to put the damn E's. So the answer is correct. In fact, C73 is the same as C74. So the answer is C7. I like S's. I like just the smaller number anyways, even though it's going to give us the same answer. C73 is C73 is 7 factorial divided by 3 factorial times 7 minus 3, which is 4 factorial. And the alternate answer is C74. See, in this one, we choose where to put the 3 S's. And here, this answer is we can choose where to put the 4 E's. You don't do both answers, you only do one, but you just have to, if you have a preference between C73 or C74, they're going to give us the same answer. And why is that? Well, let's look at the mathematics of how to compute the C74. So then I put my R factorial down here, R is 4. And then to the right of that, I put 7 minus 4 factorial. But what is 7 minus 4? That's the number 3. And if we look at these two fractions, they're exactly the same. 7 factorial divided by 3 factorial and 4 factorial versus 7 factorial divided by 4 factorial, 3 factorial. The only thing is the bottoms are switched. Doesn't matter what multiplication. So that's why we get the same answer. It doesn't matter which one we do. So forget that one. Let's just do one. What is C73? Well, C73 is 35. 35 ways. There's 35 paths, what we can say. Because each word of length 7 that has 3 S's in it, there's 35 ways to fill in 3 slots with S's. So 35 paths from A to B. Okay. So now let's turn this up a little bit. Turn it up and go to the next page that talks about a variation on the same problem. So, question 9 says we have the same thing again. We're going from A in the same city grid. This is our A, this is our B. And then you are a parent walking with your child, and there is a nasty double D. What's a double D? Well, that's a drug dealer. Let's put them over here. A nasty drug dealer. Oh no! At location double D. How many paths from A to B avoid the double D? So this is one of those useful problems. In real life, this can happen, unless you don't like to avoid the drug dealer, but you should avoid the drug dealer. Okay, so we're going to define some sets. These are the paths that go from A to double D, then to B. Okay, so these are the bad paths. These are not good at all. These are the paths that go straight to the drug dealer. Well, in all the different ways you can get to the drug dealer, and then after the drug dealer, all the ways you can get back home, maybe to grandma's house or wherever you're going with your child. And then we're going to let you be the paths from A to B, just all the paths in general. So if this was a live class, which it is, I would say, why the letter U? Why did I choose the letter U? Anyone? I'm going to pretend it's a live class. Why did I choose the letter U? Speak up. Why did I choose U? Is U like some weird letter I made up? Why do you think I chose that letter? From chapter 5. It is the empty set, which is really small, but the
It's the universe.
Yes! You know, I love when you talk. It's so lonely teaching without you talking. Okay, it's the universe. Yay! So, we can do something really cool. In question 8, we calculated the size of the universe. And we said it's 35. So, the answer we seek, the size of E prime. Because what is E prime? E prime is every path in the universe that is not one of these. So, call these paths E. These are the unrighteous paths, perhaps. What is E prime? All the righteous paths. All the ways to go from your house to grandma's house with your child and avoid the drug dealer, damn it. Oh, double damn it. So we seek the size of E prime, but we know the formula for E prime. E prime's formula would be the number of paths from the universe minus the number of unrighteous paths, the size of E. And I claim it's a lot easier to count the paths from A to double D and then double D to B, like to compute the size of E. So let's compute the size of E right now. So this is exactly the very first handout we did in multiplication principle when we were going from A, and then we had the 3 buildings, Schofield, Zorn, and Schneider, and then we went to B, and then we need to go to the next thing. We had the library and something else, I don't know, Schofield, and we were like jumping like that. Exact same problem. So compute the size of E. Well, step 1, I'm going to chop this up into 2 steps and then use the multiplication principle. Step 1, the paths from A to double D. How many ways can I get here straight to there? 2 ways. Since it's really small, just count them all, damn it, with your finger. You get 6. But the more mathy way to do that is I want to choose 2 of the 4 slots to put 2 S's in. So why am I doing this? Say I went like this way, then this way, and then this way. That's a word that goes south, east, east, south. So every single path from A to double D will have 4 slots, and I'm going to put 2 S's. I'm going to choose 2 of the 4 slots. So there's 6 ways to do step 1. There's only 6 ways to choose 2 of the 4 things. You can use the factorial fraction thing to get that, or then I said just count them up by hand. So step 2 is count. So here we count paths from A to double D. So now we're going to count paths from the drug dealer to grandma's house. Now this is way wicked small. I can say, well, I have 3 blocks total from the drug dealer to grandma's house. So I want to choose one of the 3 to put my 1 single S. So that would be capital C 3, 1. And that's like crazy to use this formula for this when it's this tiny. We just do our fingers and say I can go down and over. Or I can go all the way over and then down. Or I can break it up and go over, down, over. 3 ways. Boom. Like that's too simple to count like with a formula, but that works. So I have this subtotal, this subtotal. So the size of E multiplication principle is equal to 6 times 3, which is 18 paths. So these are 18 bad paths. These are double drug dealer paths. So if I want to know how many righteous paths, well, that would be the size of E prime. And that's 35 paths total minus the 18 unrighteous paths. which gives us a total of 17 good paths, or 17 drug-free paths. So this is like a math problem and a PSA to don't do drugs, even in Seattle where it's legal. Well, the pot thing. Okay. Cool. So there we go. Yada yada. Okay, so that's, you're gonna have definitely some of these coming up in your life, but mostly in exam land. It's really hard to make a work problem that has this on it because well, the grid. I can't draw it. But it's on a test kind of problem. So this is where that appears. So the next type of problems that's going to be a main headache in your life is poker problems. Poker, poker, poker. So let's put up all these hands. If you don't know, and there's always one student that doesn't like know poker hands, but I do want to say one thing about this. So if you like, this is a full house. A full house has a 3 of a kind. But we won't call this a 3 of a kind, even though it has a 3 of a kind. We're going to call this a full house if it has a single pair and a single 3 of a kind. This is called a 3 of a kind only because that's the best thing it can be called. If number 8 was a 3, then I wouldn't call this a 3 of a kind anymore. I mean, yes, there is a 3 of a kind, but it's not. You have to say the best hand that it looks like, not the best, not just what you see. I think I don't play much poker. I believe that going right to left, this is the shittiest hand you can have, and then a 1 pair beats a high hand, 2 pairs beats a 1 pair, 3 of a kind beats a 2 pair, a straight beats a 3 of a kind, a flush beats a straight, full house beats a flush, 4 of a kind beats a full house, and a straight flush beats a 4 of a kind, and the royal flush is the best ever. A flush means all of the same suit. So this has all clubs. So if you have 5 cards and all of the top is garbagey looking like this, then it's called a flush, just a regular flush. But if the tops here have some better kind of description, for example, they can be rearranged to be in an increasing order of length 5, then we call it a straight flush. Much better than a flush. A straight looks like this, just like 5 numbers in a row, ace being the lowest. Ace, 2, 3, 4, 5 would be the lowest straight. And ace can also be the high card. You can have a 10, jack, queen, king, ace. Ace can be high or low, but ace can't be in the middle. That's called a straight, and that's a not terribly interesting hand. But if all of the bottoms are the same, then we call it a straight flush. So a royal flush just means that it starts at 10 and goes up to ace. It has these 3 royal people, jack, queen, king in there. And this is very rare to get. So the question that's being asked first is, how many 5-card poker hands are there? And not too hard to think about that. 5-card poker hands. You think to yourself, I want to choose 5 of the 52 cards. How many ways can you choose 5 of the 52 cards? But when I say the word choose, there's no question about it. The formula, the thing that starts with the letter C, damn it, right? So the total number of 5-card poker hands. Well, we know order does not matter. Since order doesn't matter, we know to use the C formula, this one, the order doesn't matter formula. And so there's a total of 52 cards. I want to choose 5 of them. How many ways to choose 5 of the 52? Well, that's 52 factorial divided by 5 factorial times 52 minus 5, which is 47 factorial. And then this is 2,598,960 hands. poker hands. So what I call a BAM, that's a big ass number. So there's a lot of poker hands. This is probably why this is very famous in those sinful dens like in Vegas. No offense to you poker playing people, all good. If you're into that. Okay. Actually, let's erase this. This is the hell out of this formula. CNR, yes. So the things that can be asked in this section, by the way, for poker, everything can be looked up. Why? Because the internet is a place that's riddled with sin, and the way to compute the probabilities of getting hands here is all over the internet. You just enter flush, count. I bet you those two words alone will give you a detailed answer of how to compute the number of flush hands. And only do that in a bind, like using Desmos, like only use it in a bind. So how many 5-card poker hands contain exactly one heart? So let's try an example. So exactly one. When we think about it, 1, 2, 3, 4, 5. Remember, I'm drawing slots, but a hand is not in any particular order. But I know I have one heart, that must be the heart, and then these be the others, the other 4 cards. So mini task number 1, or step 1, choose my heart. Some things to know about cards. So anatomy of cards, in case you don't know. There are 52 cards. Not including jokers, but that's never going to be in poker, so we don't have to worry about them. They come in 26 are black, and 26 are red. There are 4 suits. And they go heart, diamond. These are the red ones. And then club and spade. These are the black ones. There are 13 denominations. And the denominations are ace, 2, 3, 9, 10. So these are the numbered cards. The numbered ones. The numbered ones. And then the royal. The royals. It's a jack, a queen, and a king. Hey, we were jack in our class. We don't have a queen in our class. Or a king. Well, we have lady up 7 of X. So those are the royals. Those are the numbered ones. I guess ace, is that really a numbered one? I don't know. I'm calling it a numbered one because it stands for the number 1. And then, am I leaving anything out about cards? I guess from this information here, these are equally distributed amongst the 52 cards. There's 13 of those hearts, 13 hearts, 13 diamonds, 13 clubs, 13 spades. And then there's 4 of each of these, 4 aces, 4 twos, 4 threes, etc., 4 kings. Oh, okay. If you know the shit about cards, you're probably like, duh, I knew that. Okay, so let's go back to this thing. I want to pick 5 cards that have exactly one heart. Well, there's only 13 choices for the card that has a heart because of the anatomy. And now I want to pick 4 cards, but they better not have a heart. Well, if I think about my deck of 52 cards, 52 minus 13 heart cards equals 39 heartless cards. Cards with no hearts. And if I subtract 13 from 52, I hope I get 39. So there's 39 cards that don't have hearts. So I want to choose. So the number of ways to set is 39, and I want to choose 4 of them. And that could be done in 82,251 ways, or choices. So there's 13 choices for that card and 82,000 ways to pick the next card. So then the total equals 13 times 2,251, which is 1,069,263. So of the 2.5 million hands, there's 2.5 million poker hands. The probability of getting 1 heart, it's pretty good. You're probably going to most likely get 1 heart when you're dealt 5 cards. So it's almost a 50% chance. And yeah, so this was like the thinking part right here. By the way, I wrote something here like that, 39. That's the way we're going to be writing C39 for forever, starting in the next section. But it was bad for me to do that right now because we don't know that yet. C39-4. By the way, this is, you can probably type this into Google exactly like that and get this answer. Or even say 39, type 9, choose 4, just like that. 39 the number, then the word choose, then 4. If you don't want to do that 39 factorial divided by factorial times 39 minus 4 factorial jazz, after a while you can just tell yourself, I get it, I know how to do that. Now I'm just going to use Google. 39 choose 4, boom. Your calculator also has a button that looks like CNR. Find it. Okay, so full houses. So this is non-trivial thing to ask about, the number of ways to get a full house, and there's multiple right ways to do it. So let's erase the anatomy of cards. To get a full house, I need to have 5 cards that have 2 of a kind and a 3 of a kind. So count the number of full houses. So let's look at an example. Like, how about we got a pair of 5s, maybe with a heart here and a club, and then we get 3 of a kind. How about, I don't know, not 10, that's like 5. That doesn't really matter. What's here? How about 8s, 8 8s, 3 8s. This is a full house. And maybe some love here, maybe a spade. So what we notice is that chalk this. What we notice is that we have to pick 2 denominations. So maybe that's step 1. Step 1, choose 2 of the 13 denominations. And that can be done in C13, 2 ways. And C13, 2 is the number 78 ways. And then step 2, so now let's say I picked a 5 and an 8. If I picked 5 and an 8, if I chose that, does that tell me that I have a pair of 5s and a triple of 8s? No, because maybe I have a pair of 8s, triple of 5s. All I did was choose 2 denominations. Now I have to decide which one is which. So there's 2 ways to decide which denomination is 2 of a kind, for instance. Once I decide which one's a 2 of a kind of my 5 and 8, then I know what 3 of a kind is. So I'm just going to decide which one is that one. So far, 78 ways to do step 1, 2 ways to do step 2. I hope everyone understands step 2. It's kind of the most left out step often when people do this type of problem. Step 3, we have to find the pseudo for that thing. So find suits for the two of a kind. For, in our example, that. I have to pick. Well, there's four possible suits for the 5s, so I'm going to choose 2 of the 4 of them. Choose 2 of the 4 suits to put in there. Or find suits for the 3 of a kind. Well, there's 4 possible suits, and I'm going to choose 3 of them. And that becomes 3 ways. 4 ways. Probably wondering how I did that in my head. Well, I'm a mathematician, but if I'm picking 3 things from 4 things, I'm also, so for me to understand how many ways can I leave one of them out. I can like leave out the heart, or I can leave out the club, or I can leave out the diamond, or I can leave out the spade. There's 4 ways. There's 4 ways to leave one thing out, which is the same as picking 3 things. So 4 ways. So we have we're done now. Step 1, step 2, step 3, step 4. The way we did this problem, there's 4 steps. If you did it another way, and there are other ways, you would have less steps or more steps. But we do the total. The total is 78 times 2 times 6 times 4, which is 3,704. That's the number of full house hands. Full house. Full house hands. Yep. That's what houses look like during the pandemic. Everybody's home. Mom, dad, brother, sister, everybody. Unless they work in a hospital, or a grocery store, or essential services, or Instacart, or yeah, all that. So that's the number of ways to do that. So why did I say there's multiple ways? Because there are. What do we do here? We chose 2 things without order, and then we decided which one is which. This is the same number as P. If I multiply 78 times 2, this is the same as P13 2. This is going to wind up being 78 times 2. Why is that? Because what am I doing? When I'm choosing 2 denominations, because I know I have to have a 2 of a kind and a 3 of a kind, so I need to pick 2 denominations. I'm picking 2 of them. I'm picking 2 of the 13, and then I'm arranging them in all 2 possible ways. So say I picked a 5 and an 8. You know, from P13 2, one of the ways is to pick a 5 and an 8. And then I have to arrange them. Is it a 5 and an 8, or is it an 8 and a 5? And that's why this does it in one shot. So if you're clever enough to just maybe think of these 2 steps and merge that into, well, I want to permute 2 of the 13, and then you can eliminate this. But I think it's clearer to do step 1 and then step 2 like this, rather than jump to this capital P function. Look at the clock before I. Well, there's a last page. I really want to do the last page. Is anybody up on the last page, rather than like doing that one page and then starting a whole new thing tomorrow? I'm going to do it since we're in video land. If you need to go, just go and then watch this part of the video later. But balls from an urn. This is number 13. So we have an urn, and we're picking red balls and white balls from it. So this is very emblematic of the web work. So maybe it'd be wise for me to do this now, even though it's due on, Tuesday, Wednesday, 5.6. Yes, far in the future. But so we have an urn. I'm very good at drawing an urn. And we have 25 balls, and they're all numbered balls. That way I can difference between 2 different red ones. You know, 15 are red and 10 are white. and I want to pick 5 balls. So, ways to choose 5 balls. Choose a sample. Sample is going to be relevant in chapter 6 of 5 balls. Well, we just did the choose thing. I have 25 balls total. I want to choose 5 of them. Ain't no thinking about this. Just 25. 5 choose 20. 25 choose 5. So this is the number 53,130. That's our sample space, our universe, so to speak, capital U. Okay, how many samples containing only red balls? So I put my hand in here and I picked it out and I have only red balls. Well, I only have 15 red balls total. Choose 5 of them. Again, no thinking zone. Number of ways to do this. Of the 15 red balls, choose 5, and that's 3,003 samples. So, is how many samples contain 3 red balls and 2 white balls? So, 2 R's and 3 whites. Well, this is step 1, I have to do that. Step 2, I have to do that. So it's a process of doing them one at a time. This can happen in, of my 15 red balls, I'm going to choose 2. And here, of my 10 white balls, I'm going to choose 3 of them. So we have 2 numbers. We have 2 reds. Oh, well, the problem says 3 reds and 2 whites. So I misread the problem. 3 reds and 2 whites. 3 reds, 2 whites. I should probably look at the page. 3 reds and 2 whites. Sounds like we're getting wine. So 3 and then 2 here. If I put this in Google or in my calculator button, 15 choose 3, we would get 455. If I put this in Google or my calculator button, we would get 45. So then the total, I have to multiply this because I did step 1 and then step 2. I did not do cases. This is definitely not cases. I did not chop up this job into 2 completely unrelated jobs. So multiply 455 times 45 gives us 20,475. Okay, so no thinking, a little bit of thinking. I chopped it up into 2 steps. Part D requires a tiny bit of thinking because it has the word at least. But we know what to do at least. That means use cases. And then the addition principle. So part D is we're going to count the samples that have at least 4 red balls. So 4 red balls. So remember, we can always do the opposite too. If this has too many cases, we count the opposite and then subtract it from the universe. But I don't know if this has too many cases. So we're picking 5 balls, and we want to know you have at least 4 red balls. So we can have either 4 red and 1 white. Or case 2, we can have 5 red and 0 white. Well, this one's easy to count because we already counted that. Samples that contain only red balls. This is C15.5, which was 3,003. Case 4, we split it up into the 2 possibilities, step 1 and step 2 again. Step 1, computing this, I'm going to choose, of my 15 red balls, choose 4 of them. And here, of my 10 white balls, choose 1 of them. This happens in 10 ways. And this happens in 15/4 is 1365. So this total for case 1, the case 1 total is 1365 times 10. In other words, it's 13,650. So I have 2 numbers. I have this number and I have this number. Because they're cases, I don't multiply them. I must add them. So the answer is the case 1 total, which is 13,650, plus the case 2, 3,003, for a grand total of 16,653 ways to put your hand in an urn and pick at least 4 red balls. Sorry for going over. I just didn't leave this last page for the just seems senseless. Guess that's all to say. Probably shouldn't block it. I'm going to turn off the screen sharing and also the recording and see if y'all have questions. Boopity boop. Boopity boop. Stop sharing. And then boopity boop. And we still have 4 people. We have 3 people. Okay. Well, no questions, I'm assuming. Eleanor, Ashley, Goo. Hey, Goo, can you stand in line? Can we talk about something briefly if Ashley goes?